Let's start. Today we are going to continue talking about self-supervised learning, focusing on contrastive learning. And mainly today we are going to focus on the theory side of self-supervised learning. But let me briefly recap what we covered last lecture. We mainly focused on one of the state-of-the-art self-supervised learning methods called Simpler. It was introduced quite recently. And the framework is that you start with an image, X, then you look into two views of this image from one augmentation family, say xi tilde, xj tilde. So these are two correlated views. And then you learn an encoder, embedding function, to map them to the embedding vectors. But what they also propose, they have this nonlinear projection map, G, that maps H's to Z's. G is often like an MLP with one hidden layer. And then they define the loss function based on similarities between pairs of Z's coming from two views for a particular image X. And we discussed the loss function. And the loss function is similar to other contrastive loss function with some minor differences. Okay. So in the paper, they have some interesting practical observations. Which improve the performance that they get at the end of the day. So one observation is that composition of data augmentation is important in self-supervised learning, at least in their experiment. I think they have looked into three families of augmentations, color jittering, cropping the image, and adding Gaussian noise. And if you do only one of them compared to composition of multiple augmentation methods, the latter works better in terms of the performance evaluated using a linear classifier on top of the embeddings that are obtained. So that's one observation. The second observation is that larger batch sizes and longer training help self-supervised learning. Right, so in supervised learning, batch sizes often are not too large. Right? So here in self-supervised learning, remember, when we are randomly selecting some negative samples, some dissimilar samples, we are doing it from the batch. And we want to have small collision probabilities in terms of if your samples are from the same class, we don't want to randomly select those samples as dissimilar, and that can hinder your performance. So that's one reason that larger batch sizes help in self-supervised learning, and they empirically observe if they let it run for a longer time, it also helps. So the third observation, which is quite mysterious, is that optimization over the projection head, the MLP projection head, which is the G function, helps. So previously, in other self-supervised methods, we have an embedding function, F, and then we get these H vectors, and then we define similarities or the similarities between H vectors that we obtain, and that's basically what has been done before. What they propose is that they apply another nonlinear function, they obtain Z's, and they define the loss function, the contrastive loss function on top of Z's. It would be okay, similar to the previous cases, if Z's would be considered as their embeddings, but they consider H's as their embeddings. And I'm sure they have evaluated both of them, and the quality of H's are better, and that's why they are doing it this way. So one justification, so it is not very clear what are the theoretical justification for adding a nonlinear projection head and getting rid of it in the inference time. But one justification that they have is the following, that if here is able to keep some information useful for the classification. For example, color or orientation of the objects. Right, so in terms of the classification, there are some correlations between some potentially non-informative features like color, orientation of the object with the label. Right? So if you have, all of the cats are somehow oriented in a particular way, if you rotate a cat, it is still a cat. But in your training and in your test time, there may be some correlation between some of these variables like orientation with the label, and having such additional variables can improve your downstream classification. And their hypothesis is that by training G, Z gets rid of such spurious correlations among the features, and therefore the classification task is a little bit harder. But H retains some of them, and therefore it can be good for the downstream classification task. That's one conjecture that they have, and this is an empirical observation, so it's a pretty hand-wavy explanation about this projection. Okay, so I'll finish the practical part by just showing some empirical results that they have obtained. The empirical results are pretty impressive. So they look at the ImageNet top 1 accuracy. When a linear classifier is trained on top of the embeddings, right? That's the evaluation that we have. So a linear classifier using on embeddings. That's the evaluation metric that we have. And on the x-axis, they look at the number of parameters in the model. So if they're using about 25 million parameters, they get, roughly speaking, 70% top one accuracy. I'm just like rounding up some of these numbers just to give you a feeling about some of these numbers. If they use 100 million parameters, they have a little bit of a better performance, 72, 71. And if they use 400 million parameters, they get, roughly speaking, 75-ish, a little bit lower than 75-ish. And it's a very impressive accuracy using a linear classifier. So what is the gold standard here? Let's say if you are using a supervised model, end-to-end training for the labels, with 25 million, I believe you get something a little bit north of 75%. So this is the performance of the supervised model. And of course, there is a gap, but the gap is smaller than other self-supervised methods that they usually live lower than the numbers that they have obtained. So this kind of shows it's a promising direction to learn the embeddings and then apply a linear classifier on top of it, and they obtain pretty impressive performances. Is there a question? Okay, so that's basically it about the empirical and practical implementations of the self-supervised learning methods. Then I'm going to switch gear and talk about the theory. So let me pause and see if there are any questions. Okay, so there's one question. Do you think that we may see a shift away from end-to-end model training? So end-to-end model training is obviously important, but here we have some, some limitations in some applications, especially if you don't have a lot of labeled data. Right? So in those cases, and in cases that we have a lot of unlabeled data, yes, self-supervised learning, I think it's going to be one of the major players in that domain. But if you have labeled data, plenty of labeled data, you do end-to-end training. Right? Did they train the linear classifier with few labeled data? I believe the number of labeled data they need is substantially smaller. I don't quite remember the exact numbers that they use. But the rule of thumb is that after you learn these embeddings, then for the linear classifier, you actually don't need many labeled data. Oftentimes, maybe 5 label samples per class, 10 label samples per class. So it is a substantial gain that you obtain in terms of the number of labeled samples that you need. Is F trained separately? Yes, F is trained. F, the embedding, is trained, as I mentioned, only using unlabeled samples, using the contrastive loss and this framework that we explained here. Okay. Can you reiterate the difference between self-supervised learning and semi-supervised learning? They're related to each other, but in self-supervised learning, we are crafting, so there are multiple differences, but the two key differences are in self-supervised learning, we are crafting artificial supervised learning methods and use those embeddings from the network in order to tackle the downstream task. But when we are learning those embeddings, we don't know what the downstream tasks are, right? So that's in contrast with semi-supervised learning, that when you have unlabeled data, some labeled data, you know the task and you try to solve that task in hand. Okay, any other questions? If not, let me go ahead and start talking about theory of self-supervised learning. There aren't a lot of papers in this domain. It's, as I mentioned, it is a pretty recent and emerging domain. So I'll start with this paper by Sanjeev's group, and then talk about some more recent results. So along the way, so the reason I started with the practical implementation of self-supervised learning is that now when we are talking about the theory, you'll see the loop, the holes in the arguments. So you say, oh, like, you know, but in practice we are not doing this. You know, this is a stronger assumption than you know, the one we have in practice, and that will help in terms of, you know, thinking about limitations of some of these theoretical works. All right, so first we need to model similar pairs, right? So in our contrastive loss, we have similar pairs, we have dissimilar pairs. So what are the modelings of similar pairs? So I'll explain how they model it, and then you'll see if it is a good way of modeling similar pairs or not. So they assume there's like a universe of images. Let's say these are a set of images. See, and there are some classes within the set of images. There's a cats and dogs. Some classes can be overlapping to one another. So each class is drawn with a particular probability model. With some probability, I'm going to pick an image from class C, C1. With some probability, I'm going to pick another class, so on and so forth. All right, so I draw one image, X, let's say from class C1, that's fine. This is one randomly observed sample that I have in my batch. Now for my similar image, X plus, I'm going to draw an image from the same class. So these are same classes. So in other words, this is going to be semantically similar to the original image. And for my dissimilar image, I'm going to draw it from another class. These are going to be my negative samples. Then I'm going to use these similar and dissimilar pairs in a contrastive loss. So that's basically the input for my semi-supervised learning framework. Okay, that's the key assumption about the underlying similar and dissimilar pairs that we have. And for the downstream task, They're looking at pairwise classification. Not hard to extend it to the multi-label classification, but let's start with that. In other words, nature picks two classes, C1 and C2. What's that probability? Because I know the probability is rho C1 times rho C2. And then generate samples from C1 and C2 and evaluate the classification loss. Of course, using a linear model on top of the embeddings that we learned, right? So that's basically the downstream task that we have. Okay, so that's it. That's the underlying assumption for the theoretical results of this paper. So what do you guys think? Are these the realistic assumptions based on the practical implementations that we have seen, or are these strong assumptions that may not reflect the true nature of self-supervised learning problem? Okay, Sai says looks reasonable. That's good. You're optimistic. Any other comments? Especially, I want you to think a little bit about this assumption, right? Similar and dissimilar pairs. How did we, in practice, how did we generate similar pairs? We did use data augmentation, right? But what is the process of generating similar pairs in this framework? Yeah, so basically they're drawing X plus similar image from the same class. But do we have in practice class information? Do we have the label information? We don't have the label information, right? So I think that's one limitation of this framework, because if we did have the label, the class information, if I could draw samples from a particular class, then I could just use those labels in a supervised learning method, right? So this assumption that you're drawing samples from the same class, therefore, is, in my opinion, is a bit strong for self-supervised learning, for the practical implementations of self-supervised learning. Obviously, when we are doing data augmentation, if the noise that we are adding to the image, it is not going to change the class label. So in a way, it somehow captures X plus coming from the same class, but we are not drawing an IID sample from distribution of the same class in practical implementations of data of self-supervised learning. Is this clear? Okay, sounds good. Yeah, I just want to mention this, but nevertheless, I think they have some interesting techniques to analyze this problem, and then after that, we'll look into more recent works that they have less strong assumptions in terms of similar and dissimilar pairs. Okay, so another assumption that they have, and this assumption is pretty realistic, they're assuming the number of samples, unlabeled samples that we get goes to infinity. So we'll just look into the population loss. And it's a pretty reasonable assumption because we can have, quite frankly, a lot of unlabeled samples. All right, so let's define some notations. Let's say L sup of F is the supervised learning loss with basically optimal head, right? So with optimal last layer. Goes without saying, but I just want to highlight it. Right, so remember in our embedding, so we have F, and there is like this head, which is a linear classifier. So here we are doing end-to-end training. So L sup means everything is optimal. So I'm, end-to-end training, the head is also optimal. They also look into a subset of supervised methods where in the last layer, I'm not going to optimize over W. I'm just going to use the mean vector for each cluster that I receive. So that's basically for each label I get some representations through F, and then I'm just going to use W, which is the mean of embeddings in a particular class label, and then I'm going to use those mean vectors in order to do the classification. So obviously it's a little bit of a suboptimal way of doing supervised learning, but they have some results for that, so I'll just mention it. So that's what they call L sup mean. If here we are using mean classifier W as its head. So two notations. And for the classification, we are going to use a logistic loss. With one negative sample. Right? You often actually have more than one negative samples, but that's the starting point. K is the number of negative samples. Per image. So the loss is going to be something like this. It is very similar to the sentence embedding loss, that we take samples X and X plus from similar classes, X minus from another class, and then we look at log of 1 plus e to the power fx transpose times fx minus fx transpose fx plus. It's exactly the same loss function for the sentence embedding. So using these notations, they have a couple of results. So the first result says that if I look at the supervised loss of F, but not optimal supervised loss, I'm going to just look into the mean W as my linear classifier on top of the embeddings. That can be bounded by some constant factor of the unsupervised loss for every F in my class. And what is the tau here? Tau is usually small. It is the collision probability for pair of random classes. As I mentioned, in the definition of similar and dissimilar pairs, classes can be overlapping. Tau indicates the collision probability. It is usually small, right? So if tau is small, then what you get, tau is small, what you get is on the left-hand side, your unsupervised loss, you train F, and then you train an optimal linear classifier on top of it, right? So that's basically the unsupervised loss. Upper bounds, your supervised loss, but not exactly the best supervised loss, right? So the caveat here is that the last layer in the supervised loss, it is the mean. And you can kind of see it is a trivial result, right? Because in unsupervised loss, especially using this, you're somehow clustering your points. And similar and dissimilar pairs comes from the same class versus different class. And when you're looking at just the mean, it is the mean in each cluster. So you can see where this result is coming from. So it is not a surprising result in general, but it's good to, it's a good start. Okay, so let me pause and see if there are questions. F is not trainable. Saksham, I am not sure which part you mean, but in general, F is basically we train F, right? So either in unsupervised using unlabeled data, in supervised, it's like end-to-end training.
So I just meant like once we train with the self-supervised training, it's kept fixed, right? When we're training with classifier.
Yes, you use unlabeled data, you train it, and then apply it on top of an optimal linear classifier to do the supervised task, but then you're not touching F, right? So that's the whole point. Yes.
Thank you.
Okay. So that's their first result they have. But what would be the ideal result? Ideal result would be if you pick F star comes from your unsupervised problem. This is the minimizer of unsupervised loss, and then on top of a linear, of course, a linear classifier, an optimal linear classifier. If you evaluate that F star in a supervised setting, ideally we want that to be better than any other supervised F, right? So that's basically the ideal situation. In other words, in that case, we have just a potentially loss of a performance with a small constant number. And they have some counterexamples. You can look at the paper that they show in general it is impossible to get this for a general class of functions and tasks, right? So they have like a very simple example. I'll just let you look at the paper for that. And they show if there are some stronger assumptions. For example, if the embeddings are tightly clustered and they're far from each other, then you can have a result like this. But in practice, I'm not sure how how realistic this assumption is. Right, so that's basically the gist of the results of this paper. Are there questions? Okay, if not, I'm going to switch gear and talk about another recent paper by Tosh et al. It's a pretty recent work. And this work is closer to practice. And we'll see what kind of results. So that's why I didn't spend too much time on the first paper. So this work basically connects the problem of self-supervised learning with the problem of multi-view representation theory. Presentation. Okay, still there are some caveats in the setup of results for this paper as well. I'll explain it, but I think the assumptions that they have, they're more realistic assumptions compared to the first paper that we covered. All right, so they start with this setup of having two views of the data. Let's say X and Z, they are two views, and Y is my label. So these are two views of the data. Let's say if you have an image, maybe an augmented version of that image, there'll be two views of the same sample. And Y is the true label. If you have a cat, augmented version of a cat, and Y would be the cat label. Okay, so the key assumption that they have is that X and Z, the two views that we have, should share redundant information with respect to the label Y. So what do I mean by that? In other words, if I predict Y from just X or just Z, should be as good as predicting Y from both of them. So X and Z there, they have basically, roughly speaking, the same information content with respect to the label. And that's realistic, especially if you're looking at, augmented version of one image to another, they represent the same image with respect to the label. So in other words, predicting Y from X or Z individually should be nearly as good as predicting Y from both of the views. So remember, we are not assuming we have labels in training self-supervised model, right? So that's not the assumption. The assumption here is that the two views, they have a lot of correlated information with respect to Y. Right? So even if I have both of them, and if I had labels, I don't have labels during my training, but if I had labels, if I use both of them, it wouldn't really help compared to the case that I have just only one of them. So that's the key assumption for this work. And I think that's a more realistic assumption. So if you want to quantify this, so you can think about, okay, so what is the predictor of Y given X and Z? So that's the joint predictor. It can be nonlinear function, pretty complex function, doesn't matter. And let's look at an individual predictor of Y from an individual X, right? We are not using Z in that case, and that would be the error that we get. So this error, let's call it error of X. That's the error that you only use X in your prediction compared to if you use X and Z in prediction of Y. Similarly, you can define error of Z if you have both of them in prediction of Y. You only look at Z. And that is the error with respect to Z. So the assumption is that these two terms, they're small. Right? In other words, it really doesn't matter if I'm using both of both views or one view to predict y, I'll roughly speaking get the same accuracy. Okay, so using this assumption, they use a formulation of contrastive loss or contrastive learning as an artificial classification problem. As an artificial, quote unquote, classification problem. Remember, in the, let's say, previous paper or even in the practical simpler implementation, the problem was like kind of a regression problem, right? In the contrastive loss. So you had like two embeddings, you look at the similarities, and then you try to maximize like cosine similarities between the embedded vectors coming from the similar pairs. But here they're using contrastive loss based on classification problem. Basically that here's the loss. So you have two views, X and Z, for an image, say X, an augmented version of X. You label it as 1, and then you draw a random sample, a random Z that is not paired with X, and you label it as 0. So these are dissimilar pairs. And then you just solve a classification. So this is a two-way classification problem. Classify between the two. So these are artificial labels, remember. So it has nothing to do with my true labels. I don't have true labels in my training. I have X's and Z's. So these are same views of an image. These are the Z tilde is a random Z I'm obtaining from my data. And then I just train a classifier, and I'm going to look at the penultimate layer of this classifier as my embeddings, right? Potentially. There are other embeddings, so we'll talk about that. But that's basically the idea. So if you solve, so this classification loss, you minimize classification loss. So what is this? So the function is a function of X and Z, right? So your classifier inputs a pair, X and Z, and outputs a number. That number tells me if these two pairs are similar or coming from similar views or different views. So therefore, the optimal classifier would be a function of X and Z. So that's something that we call with G star, X and Z. Now, if I train this optimal classifier, then you have you give me two pairs. And if the output is closer to 1, then I'll say, okay, good. So that is the comes from the similar views. If they're different, it should it should output as 0. So if you write this up, it's actually not difficult. You use a logistic loss. You get this closed form solution for your G star based on the distributions, joint distribution of X and Z. Again, this is a function of X and Z. So you get the joint distribution divided by the product of the marginal distributions. That is the optimal G star that you can obtain. Okay. Let me pause and see if there are questions. how are you combining X and Z to predict Y? I'm just gonna, have a classifier that inputs both X and Z, right? Concatenate them. And Y would be my label if they're similar or different, right? So that's basically the case. Right. Any other questions? Okay. How do we know the marginal distributions, and or assumption tells us they should be similar, right? So we know the marginal. Like the assumption is that we know the marginal distribution because you at least you have samples from the marginal distribution. We don't have the labels, but we know the distribution of X and the distribution of Z's because these are unlabeled samples. There are assumptions. If you have only some limited number of samples, they analyze some approximation errors in the paper. But let's assume we have a lot of samples, so we know these marginal distributions. Okay, GXZ is 1 if X and Z are independent, yet they have redundant information. Okay, so XZ, if they come from two views of the same sample, they have redundant information. Otherwise, they're like independent. And I want to like discriminate between the two, right? So G, I want for one case assigns 0, the other case assigns 1.
Professor, so
Yes?
you're trying to discriminate between two different views of the same class?
Okay, so let me give you an example. Let's say you have a cat, right? And that's your X. And then you maybe augment something, to this. It's still a cat, right?
Yes.
So that is your Z. So that's basically X and Z pair. And then you have another cat, the same cat, right? That's X. And then for this, you randomly, this Z tilde comes from selected randomly from just PZ. From your data set, you augmented all samples, with some noise. Just pick a random sample. And with a high chance, it is not going to be the same cat, right? So it may be like a dog or something else.
Yes.
And then we want to classify between these two. So I want to train a function to tell me if the two pairs comes from the same, two views of the same sample or different samples.
So in the first sample, X and Z are not independent, right?
No.
Which means the G star score would be low. It wouldn't be close to 1.
Low or high, right? So I just want to discriminate between the two. It really doesn't matter.
Okay.
It's a binary classification, right? So you label them as 0 or 1, doesn't matter for me.
Okay.
Okay. All right, so let me move on. As I mentioned, the assumption is that X and Z, they have redundant information about Y. Right, so that's the assumption. Therefore, if we first predict Z, so if I'm just getting X, no, I'm going to do the following. I'm going to predict Z first and then use that in order to predict Y. It should be a pretty decent way of doing this, solving this problem. But if we first predict Z from X, then use the result to predict y, it should be good. Should be good. Okay, so let me write that in a more mathematical way. So that prediction, this predictor, is going to be called mu of x. And the idea is that this mu of x, if they x and z, they have shared redundancy with respect to y, it should be a very good predictor, even though it only depends on x, not x and z. So in mu of x, the definition, the formal definition is the following. So I'm given an x, then I'm predicting z, and using that z, I'm predicting a y. So I'm just going to look at prediction of y given z. So let me open this up to be very clear what we mean. So I have an integration. So I can obtain maybe very different values of z. Z would be a distribution depending on the value that we predict. What is that distribution? That's the distribution, conditional distribution of z given x. So for a given x, I'll have a distribution on z's, and for each of them, I'm going to predict my value of y, take the average based on the probabilities. That's basically this predictor. So let's write this conditional distribution, pz given x. I can just use the Bayes rule. So that is p x and z, xz divided by px of x. Right? So that's basically this term. So you see now we are getting close. So this term is close to my g star, but there's a missing term. Right? In the denominator, what is missing? Yes, I'm missing pz, right? So I'm gonna multiply with pz of z, and I'm going to divide by that. It's basically the same thing. So therefore, I can write this whole predictor as ey given z times, what is this? This is my g star of x and z, pz dz. Okay, just like a warm up, you know, we are not even tackling the problem yet. It's just a predictor. I predict z from x and then y from z. Now the first result that they have is the following. This predictor is good if x and z, they have shared information. So if I look at the difference between mu of x and a joint predictor of y, when it has both x and z, the error is small. This predictor is good. And the error can be bounded by sorry, so Zoom got disconnected for a second. Can you guys hear me?
Yes.
Okay, so that was weird. Okay, so let me. Okay, do you guys see my screen? Okay, good. So Zoom glitch. Okay, so if I use mu, compared to the case that I have x and z, both of them, it's a good predictor. So the error can be bounded by epsilon of x, defined earlier. So these are small numbers, plus epsilon of z, and plus 2 times epsilon of x times epsilon of z. Very simple proof actually, but I'm not gonna bother you with that, so you can look at the paper. Okay, so that's basically one of the elements that we need. So we haven't talked about embeddings and stuff, right? So the things that we have here is that assumption is that x and z, they have shared information with respect to y. Therefore, if I come up with a predictor like mu of x, when I first predict z and then I predict y using z, that predictor is pretty good. So now the idea is that, can I use my embeddings? I'm going to define some embeddings in order to get a predictor close to mu of x. If I get that, then I'm done, right? Because I know mu of x is close to the best predictor of y using both pairs x and z. So that's basically the game that we are going to play. Are there questions? If you have typed your question in the chat box, for some reason everything is basically cleared out, either type it again or unmute yourself and ask your questions. Okay, so let me carry on. So the first embedding that they consider is an embedding called landmark embedding. It is the following embedding. So in our unsupervised part, we train G star. Remember, right? G star is the classifier, classifies between two pairs if it is the same B or different B's. Right? So G star is something that we have, is computed via contrastive learning. Now I have this G star. I want to find an embedding. You give me an image X. I want to say, okay, so this is the embedding of X. So how to embed X? Because G star, remember, it has like two pairs, X and Z. No, I just want to find an embedding for one image, right? That's the goal. So in the landmark embedding, they do the following. They say an embedding of X is G star of X. And then for the second pair, I'm just going to use a random Z. And then I'm going to generate another random Z. And I'm going to repeat this M times. And I concatenate these numbers. Remember, the output of G is a single number, right? So this is a single number. Single number. So it's going to be a vector of length M. I'm going to use that as my embedding of X. Okay, so these are randomly generated from property of Z. Okay, that's going to be my embedding. Okay, in practice, we don't use this embedding, right? But it's an interesting embedding, and you'll see theoretically it has some good properties. Okay, so we'll say basically phi, this is going to be a good embedding if I train a linear classifier on top of it. I get close to mu of X. Remember, mu of X is a good predictor for me. Right? It's close to the joint predictor of Y given X and Z. So if I train a linear classifier on top of phi, the embeddings I have, I get close to mu of X, I'm done. It's a good embedding if Okay, I'm sorry, guys. I think there's some internet connections, some issues about internet connections today. Okay, so hopefully in the remaining 10 minutes, we won't have an issue. Let's carry on. Okay, we say phi is a good embedding if a linear classifier of phi approximate mu of x. Mu of x is a good predictor of y for me. So in other words, I want to see if there is a W such that W transpose phi of x is close to mu of x, because then I'm done, right? Mu of x is a good predictor. It's a good predictor of y. And in fact, that is the case. So if you, if there's a construction, explicit construction of this W weights that shows a linear function of phi would be close to mu of x. So what is that construction? W is a vector of length m, right? So Wi consider as 1 over m expectation of y given Zi. Zi is one of these samples that we have generated. So in that case, W transpose phi of x would be, okay, so I'll just multiply. So it's a vector. So it's 1 over m, sum I1 to m, this term, y given Zi, times basically the ith element of phi, which I know is G star x and Zi. Okay. Now, if m is large, if m goes to infinity, the summation would converge to an integral. So I'll basically have an integral of y given z, a particular z, times g xz pz dz. Okay, what is this term? That's mu, exactly. So this is exactly mu of x. In other words, if I have m large enough, then a linear function of this phi landmark embedding would converge to mu of x, which already I know that's a very good predictor of my label. Therefore, the embeddings that I compute, they're pretty good. But you can say, in practice we don't use it, right? So it's a good theoretical embedding, but we don't use this in practice. So they also look into other types of embedding. So one embedding is called direct embedding. It is closer to a practical embedding. So here, instead of learning a bivariate GXZ, GXZ, we are going to learn a function that is a product of two functions, mu x transpose times psi of z. And then I'm going to use just maybe just mu of x as my embedding of x. Here, I want to note that in this way of embedding, embeddings of two views of the same data are different, right? Can be different. So these are two different functions. For looking at embeddings of xn, it is maybe augmented version. Okay. All right, so for this, they have the following lemma. It says for every pair of functions, let's say mu, from x to, again, embeddings are m-dimensional, psi from z to m-dimensional. There exists a linear function w with coefficients w in m-dimensional such that if I look at the linear function of just one of the functions, mu of x, w transpose mu of x, that is actually close to the mu of x. Eta of x, that's close to the mu of x. That's mu of x is the best predictor that I have. Right? So if I look at the error that I'm going to see, that error is bounded by what? The variance of y, that's the constant, times an error called epsilon direct, which is a function of eta and psi. And what is this epsilon direct? That is just the difference between eta times transpose times psi and my optimal g that I would obtain without having this assumption that my bivariate function is from this particular form. Okay, so here's the expectation is over x and z comes from the product of two distributions. So in other words, this lemma tells me as long as the case that this eta of x transpose psi of z, it's a particular bivariate function, right? It's not as general as gxz. As long as this is close to g star, then I'm good. I'm not losing much information. And I, in fact, can use a linear function of one of these functions in order to get close to mu of x, which is a very good predictor of y. That's basically the idea. But the question is, okay, so can we get this? Can we write g star x and z as eta of x transpose times psi of z? Okay, so I think this should be z of x. So we are losing some information, right? In general, we may not be able to do it, but if we could write it that way, then we are done, right? Because with this lemma, it says the error of a linear function of eta of x compared to mu of x, which is a good predictor, would be very small. Okay, so this holds under several conditions that they have considered in the paper. So let me explain them. We are running a little bit of late, but let me finish this. So they're assuming if there is like a hidden variable h such that x and z are conditionally independent given h. This assumption can hold in general that we can approximate G star using a product of two functions. So they look into two cases. One is that this h that we have is a discrete random variable. It is not practical, not realistic, but it's a good warm-up assumption. H is a discrete variable. In that case, in fact, G star can be written exactly as some functions eta star of x times psi star of z, then I'm done, right? So that's exact. No approximation, no nothing. And then I can use this lemma to show that, okay, so this error is in fact 0, then I have W transpose of mu of x would be exactly, the same as eta of x would be exactly the same as mu of x. So here I'm done. But then discrete H is not a practical assumption. So they have another case where the assumption is that x and z, again, they are independent from each other given H. H can be here, it doesn't have to be discrete. So they show, in fact, there always exist, they're not constructing it, but they say they exist, eta and psi functions. These are embeddings, such that that assumption that we want holds, right? So we want eta of x times psi of z is close to G star of x and z. Without explicitly constructing it, they show it is, there are some other terms, but when the dimensionality of the embeddings increases, the error decreases. Embedding dimensionality. So that assumption approximately holds. So this is order of 1 over m. So W transpose mu of x would be close to mu of x with order of m. And we know mu of x is a good predictor of y. And that's basically the final result of this paper. Okay, so that's all I have. There are some other works in this area in terms of looking at the theory of it. So there's another recent work by Lee et al. Came out a couple of months ago. They're also looking at some assumptions, independence assumptions between x and z given y. That's a little bit of a stronger assumption than the one considered in the paper that we talked. But those are also pretty good reads. All right, so let me pause and see if there are any questions.